This is the third layer, if you remember the whole planning architecture. And in this, so the most commonly used techniques are called discrete motion planning techniques. And in this discrete motion planning, we have two things. One is deterministic sampling and one is random sampling. What is deterministic sampling? So deterministic sampling is something that you want to sample every point every 10 meters and you want to go check if you can drive or not. And in the random sampling, we will be more looking at, you make a sample somewhere, anywhere, and then you try to add it to the path and see how it goes. We will look a bit more about these two things, deterministic sampling and random sampling, in the next slides. So it will give you a more idea. And also you get how does a trajectory look like also in the future. So before we go learn about the trajectory planning, let's remember these 5 points. How does it work? So it's called, first thing is sample. Next one, you connect the samples. Then you evaluate the samples if they are fine. And then you finalize one of the sample that you have done. And in the end, you repeat the process again and again and again. So let's look at one of the trajectory planner, which is an RRT based trajectory planner. So let's start with this. So this is a graph-based planner, and most of the planners are graph-based. So I think it's a very common thing. It's a good idea to know a little bit more about graphs before we tackle the problem of planning. So we have the car. So we initialize the graph. So we have a car and we say that, okay, I want to make K samples or 100 samples. Then we create a sample in a random configuration. So in this planner, this is the planner used by the MIT vehicle in the DARPA Urban Challenge. So they were sampling in the control space. Control space is steering and acceleration. So they said that, okay, I want to apply 1 meters per second square acceleration and then steer to left or steer to right. So these two are the first two samples that we see on the bottom orange dots. So if we apply this to the car, so you have two things. So the green line on the red line. So this is the red line. This is in the state space, or how the trajectory will look like. So the robot will go ahead till here, and then next again we make two more predictions from each of these. So if you can see here, so these two are the 2 points that are initially sampled. So that's the creation of random config sample, and then they're connected to the nearest graph, so which is the car. They're connected here, and then this edge is evaluated. So if this is drivable or not. So we can see that this is the point, like till here, we say, okay, it is drivable, both are good. And from here, again, 2 more samples are created. It's a repetitive process till we reach the goal. So 2 more samples are created, which are here, these two. And now when we expand the trajectory, like if we say that, okay, so this is driving to the left with 2 meters per second square acceleration. So the vehicle is driving into the other lane. We don't want to get into the other lane. So what we do is that we mark this trajectory as a bad trajectory. So stopping node. And similarly on the right, if we see there are 3 more samples, and one of these samples drives into the obstacle. So we don't want this trajectory as well. So we mark this as a bad trajectory. So on and on. So each of the sample is made, and then the sample is checked till it reaches the goal. And then we identify this green line, which is the trajectory that we want to follow into the future for the vehicle to avoid this obstacle and go forward. So this is an RRT based planner. This is a very efficient planner, and a lot of places this is used. It's also used for ground robots, aerial robots, and also the robotic arms and so on. So this is very important to learn something like this and to use it in the industry. And the next one is the Lattice planner. So this is a deterministic sampling. So how does this work in a Lattice planner? In the deterministic sampling, so we make points into the future by fixed configurations. Like, so in this one, these points were generated randomly. You can give some constraints and call a rand function, and then you have these points. And in here, you are calling them with a fixed configuration. Like, so if you look at the trajectory on the left side, here you can see that we have a car, and we are making some samples ahead of us. So the gray cars are the samples in space. So we want to say okay, I want to sample at 10 meters ahead, 20 meters ahead, and 30 meters, or at sample at every 10 meters distance. So that's what we see on the right. So we have the car which is at 0, and then we have a sample at 10, the green dots at 20 and at 30. And next, you can go from this point to this point, 0 to 10, with different speeds. So the current speed is 6 meters per second. I can say that, okay, I can go from 0 to 10 with 0 to 6 to 0 meters per second, or 6 to 2 meters per second. I can decelerate, or I can continue with the same speed, or I can accelerate and go to 10 meters per second velocity. So this is the velocities. You said you are choosing 6 velocity profiles and also 3 space profiles and also 2 direction profiles. So each one is in the left lane and the other is in the right lane. So now we connect these dots. So from here you have 6 options. You can go to 10 meters with these velocities. And from here again, you can go to the next 20 meters with few more options, like again with the 6 velocities and so on. So we connect all these points, and each one from here till here, whichever goes to the end, will become a trajectory. So now it's mn trajectories. So we have like 3 samples, 6, 18. So these are like mn factorial trajectories, if you more of permutations, and then we expand this. So basically with this small space that we chose certain velocity profiles, certain distance profiles, we are able to create so many trajectories that you see on the top. So, and now all of these trajectories are evaluated and each one is checked, and then the best one is selected. So how to choose a best trajectory? What is a good trajectory? That's what we will look into in the next slide. Before that, so let's look into the trajectory evaluation, then we look into the trajectory representation. So how is the best trajectory evaluated? So these are evaluated on the things like path length, how far is it? What is the curvature, that you don't want to drive like two sharp curves, and the rate of change of curvature, and the lateral offset to the closest center line, that when we are driving the vehicle on the road, it should be close to the center line, but not between the lanes or something like that. And if there are obstacles in front of us or beside us, we should maintain certain distance to these obstacles. And the next one is the duration of the plan, like how long this plan can be executed. Like if it is only for like next 200 milliseconds, you don't want to execute, it should be a bit longer. And what is the speed, what is the acceleration, what is the jerk, and the centripetal acceleration, so that the drive is comfortable. And all of these are mainly divided into these 5 categories. So collision detection, collision checking, kinematic feasibility, reactiveness, efficiency, and comfort. And these are rated in the same order almost, because the first most important thing for the trajectory, that it should be non-colliding, so that the trajectories are safe. And next, it should be feasible kinematically, and it should be reactive, efficient, and comfort. So this is how the trajectories are evaluated, and the best one of this is used. Let's look into the trajectories, how they are represented. So we saw these lines before, so something like this, or here. So what are these lines like? How do I represent these lines even? So generally they are a set of points, and we can represent the set of points using splines. Splines are polynomials spread across the whole point. So there is a polynomial for each of these 3 points, and then they're connected. Or we can use just the polynomials. So the splines make it more close to the representation compared to polynomials. If you right side top, if you can see this picture, the green one is a polynomial and the blue one is a spline, and the points are the circles. So if you can see that the blue one follows more close to the points compared to the green one. So the polynomials are efficient for a small time, but if you have more samples, splines make much sense. And also we know that the cars cannot drive in any direction or any angle we want. So they can only drive with certain curvature or certain speed, etc. So we also, there are a lot more representations of trajectories. One of them is called Dubian paths, in which it is represented using curves and straight lines. So this is more like, okay, the radius of 6 meters or 10 meters for an arc length of 10 degrees, and then followed by a straight line, and similarly again one more arc length and a straight line. And or there are the one more thing that are used is reed sheep curves. So these curves also help in the reverse direction. Here we can mention the direction of the curve so that we can take like a reverse. So when we are changing the lane, we go back here and go front. So this is something that you could have observed when you are performing a U-turn, etc. on a road. If you're clear with these concepts, the trajectory representation, the trajectory creation, and the whole planning concepts, let's look into one more thing, collision detection. So how do we do this collision detection? What is inside this? Because all the trajectories must be collision free. So I think I'll just go through a little brief about this here. So if you can see on the leftmost slide here, we can see that there is a car. So let's imagine this is something like this. So the car is shrunk to a point size and the whole environment around it is expanded to the size of the car. So that what we are moving is a point, but the whole environment is expanded to the size of the car. So that now you know that if the point touches any of this environment, it's a collision. So we have the trajectories which are represented, let's say, by certain polynomials, and we can check if any of this polynomial touches any of these blocks. This can be like represented as small circles or small squares. We can check if any of this is intersecting with any of this environment, then if there is a collision. If there is no intersection, there is no collision. So here you can, as you can see, the blue line is a collision free trajectory which the robot will follow. Or one more thing that we can do is we project the path of the car or the car into the future and then see if there is a collision anywhere. So we just say, I move the car here, I place it at 0 meters, 1 meter, 0 meters, 1 meters, 2 meters, 3 meters, so on, and see if it is colliding with anything in the static environment. And the next one is the collision detection in the dynamic environments. This is a bit more tricky because we also need to see in time where the other objects will be in future. So here you can see that, let's say, for the next 2 seconds, this is the trajectory of the car, this is the trajectory of the red car and another red car. So if we draw a box around it, we know that, so in the next 2 seconds, the paths of these two cars are not intersecting. And if for the right side, the bottom car and the right side car, we see that the trajectories are intersecting. Now we can do something like the forwarding, but in the time, not in space. But we can say, okay, at 10 milliseconds, the cars are represented in the blue with these blue and red circles. 10 milliseconds, they are here. 20 milliseconds, they are here. 30 milliseconds, they are here, and so on. Then we can see maybe at like 100 milliseconds, they are colliding with each other, or 2 seconds in the future. So we say, okay, there is a collision. And sometimes instead of circles, we can also forward the exact shape of the car and see if there is a collision or not collision. Circles is much more efficient in calculations compared to forwarding the whole car dimensions and checking for collision. And the last thing about autonomous driving we will speak about is the evaluation. So how did it evolve over the times? I think one of the first projects for autonomous driving was Eureka Prometheus. It's an European Union project, and it was driving this the big truck on the left side autonomously on the German autobahns. And this is not super autonomous if you look at the current standards, but for the time it was one of the most advanced, and that was able to do a lot of things autonomously without driver interaction. And I think the big push for the autonomous driving came in 2006, 2005 to 2007, where 2008 actually, where DARPA conducted a series of challenges on the autonomous driving, like the DARPA Grand Challenge and the DARPA Urban Challenge, where a lot of universities and research students from all over the world participated in these competitions for huge prize money, and also to make the first autonomous cars. And in 2017, Audi A8 is the first commercially available level 3 autonomous car, but it comes with a limitation that it can only drive at 60 kmph and not at a high speeds. But in 2020, in the current state, all the major automotive companies are promising autonomous driving. And I think in 2022 or 2020, end of 2021, we will have autonomous cars which will drive autonomously on the highways. And by mid of the decade or end of the decade, hopefully we will have the autonomous car at a full space in the whole world. Let's go to the next one. Let's look at this small demo, and then we see the concepts that we have learned before being applied here. So this is an example video from Zoox. It's one of the companies that has working in the field of autonomous driving. And as you can see here, so the blue things are the objects that are represented in the environment and that the car is seeing in front of it or around it. And the environment, if you see, it's a bit more dense, like it's compared to your normal Google Maps. It has lane markings which are telling, okay, this is a dashed line, this is a bicycle parking lane or a parking lane, and there's a footpath, and there is a zebra crossing or so on. It's also showing the traffic lights if you see. So this is the information in the HD maps. And then it's also making decisions like whether to drive or not to drive. Like here, if you see, so there was a big truck. So the car has to maintain more distance to the truck. So it has moved slightly to the right side, but still following the rules. And then we see there's red cones, etc. So it doesn't want to drive on those red cones. And also like the right lane, this is a bus lane, or so you can see with this red marks that, okay, this is not accessible for driving, so on. So let's go to the next one where we see the similar in the path planning for the normal robots which are used in the industrial robots or in the warehouse robots, because warehouse robots have become a So the warehouse robots have become a huge thing currently because of a lot of processing of online orders and so on. And also these are the used in the industries in the manufacturing plants to transport things. And this is also one of the major growing sector in the current times. So, and these robots are working in collaboration with humans, and they're making the plants and everything more efficient. So as you can see, there are different things that are happening here. I think we can fast forward a little bit here. So we have these sensors that are looking for obstacles, and also to say, okay, what is if it's a restricted area? Generally, this is the job of the route planner on the top level to not to enter the restricted areas, and also to look for pedestrians, which is the same as autonomous driving, and also to change the course of action if there is an unexpected environment, etc. And also localize here. The localization is also very important because we should be able to pick the boxes or something very efficiently, that because these are of exact dimensions and we should be moving them in the same way. And let's look at one second, I think. So let's look at the last things before we go complete the whole presentation. How is the market for the robotics, and is there going to be a growth or not? So currently, this is excluding the autonomous driving because it's hard to predict how many of the vehicles that will become autonomous in the future. But I think this prediction for the robotics market, which includes industrial robots, co-robots, service robots, and other, is pretty much accurate, and this kind of shows the how it will be in the future. So we will see that currently the industrial robotics market is at 22 billion, and it's expected to reach 67 billion in the next 8 years, which is a huge growth and which is a huge scope for the robotics engineers or enthusiasts. And also there is an increase in the cobots, service robots, and others like space robots and in the service industry. Let's look at some of the companies that are working in the different fields that are providing opportunities if you're having knowledge in this domain, in the planning or in the robotics domain. So one is the autonomous vehicles. All the big brands or all the automotive companies are having plans for the autonomous drivings in the future. So there is a huge opportunity here. And the next one is in the agricultural robots. There is a more and more demand for agricultural robots as the labor is becoming more sparse and more costly. So there are robots for picking up apples and tomatoes, etc. And there are also a lot of big machines which are actually harvesting. but we need more precision in the picking up of the fruits, etc., because the trees should not be harmed. But in the harvesting things, mostly the things are uprooted and they are harvested. So there's a huge difference. So there is more control and more precision. And we also have industrial robots like uh, Siemens, ABB, and Fetch. We have warehouse robots. We have home robots, which are also gaining a lot of popularity, like vacuum cleaners and gardening robots and so on. Also the support robots for the elderly and also for children, like Aibo we are doing. And also there are a lot of hospitality robots which are coming into the market now. Something like Pepper, which is from SoftBank. I think it's a huge thing and it's being used in a lot of industries currently. And IBM Connie. So these are some of the robots. I did not list everything, but there are hundreds of companies working on the robotics and there are a lot of opportunities in this domain.